Welcome to this video. Today we are going to see about ideals. So ideals are ubiquitous actually, and they are used everywhere, whether it is algebraic number theory, algebraic geometry, or commutative algebra. They are used everywhere. But in this video we are going to see the concept of ideals from a very category theoretic perspective. The construction which we'll be doing here will be a sort of generalization of the construction of the quotient ring by a two-sided ideal. So let's start. So first of all, let D be a pre-additive category. Pre-additive category means the home sets are actually abelian groups. Abelian groups, and the composition maps are Z bilinear. So that is a pre-additive category roughly. So what is an ideal? Now let's define an ideal. So what is an ideal? Is an ideal. So an ideal I in D, this is not a set. Actually this is a class. Consists of the data. And what is that data? Let me write. Consists of subgroups of the form IAB. Actually they are the subgroups of the home set. Home set is actually an abelian group, so these are subgroups of an abelian group. That's the beauty of an pre-additive category. Subgroups with a condition, and what the condition says that condition. So the condition says that for any morphism, we are going to take two morphism. First one is F, which is from A to take it A naught to A, and another morphism from G which is from B to B naught, and we have taken an element U from IAB. So the condition says that we have UOF so U composed with F is a morphism inside this subgroup, and this is an element from this is inside the home set from A naught to B, and GOU will be inside I of A comma B naught. So that was the condition inside this ideal I. Ideal I is a structure which consists of this entire data. For any morphism, we have taken any two morphism from the pre-additive category. Here A and B are from objects of category D. We have taken two morphism F and G in this pre-additive category, and we have taken an element from this subgroup. So this with this condition, this one, this is the whole structure forms an ideal. That is what the definition of ideal from in the pre-additive category. So if we have constructed an ideal, then it is a natural question about the quotient structure. So we will going to see about quotient category. So we are going to see how our quotient category will look like. Surprisingly, it looks very obvious. So if it is a category, then it has an object and morphism. So let's first talk about objects. So the objects of the quotient category actually same as those in category D. And if I talk about morphism, this is about objects, and this will be about morphisms. So morphisms will be determined by the quotient groups. Actually, what I am saying that for any objects A comma B in preadditive category D, the morphisms in the quotient category D over I are given by the quotient groups. That means we have a home set. The morphisms between the two objects in the actually objects are same. We have seen that earlier. So in the property one, so in the quotient category, the morphism between A and B will be defined as okay. So this is actually a quotient group because home and this home set actually it was an abelian group because our category is a preadditive category, and this was the subgroup of this group. So as it is an abelian group, subgroup quotient by a subgroup will obviously form the quotient group. So moreover, I want to talk about compositions also. So the composition of morphisms in the quotient category of morphisms in the quotient category D over I is induced by the composition in D. Now this is now actually behaving like a preadditive category 2. So the composition of morphisms in this quotient category is induced by the composition in D. That means it ensures the quotient structure that respects the original category composition maps. So that was all. So now we talk about the functor from the category to the category preadditive category to the quotient category. So the functor we have functor Q from the category D to the quotient category. Now they are actually both preadditive categories. Is a canonical quotient functor. Is a canonical quotient functor. In group rendering, you actually call this a projection map, but here we are going to say it is a canonical quotient functor. This functor has a very special property that it acts as the identity on objects. It will act as an identity on objects in this preadditive category D, and maps each morphisms in the preadditive category D. That means what I am saying that it will Q will map objects will map objects uh, as an identity functor it will Q will act on the objects of uh, D as an identity. But the interesting thing is about morphisms in the preadditive category D. So uh, a Q will map each morphism, and morphisms are where from the home set, each morphism from the home set to its equivalence class, actually to its equivalence class. This functor is additive moreover because it respects the additive structure of the home set. So that was all about the functor, the canonical quotient functor. Now we will see the universal property. So universal property. We will see the whole universal property behind this categorical construction. Actually, whenever we do any categorical construction, we study the universal property, either it is direct limit or inverse limit or a co-product or whatever it is. So let's see a universal property. So given any preadditive category, we have a we have taken a preadditive category D, and we are taking F a functor from the category D to the preadditive category D to another preadditive category D prime. Okay, now if F F is a functor, F maps this morphism F, small f 0, for every F from this subgroup. If this functor takes this morphism, the morphism is from the subset of the home set only, which is a subgroup here, then there exist a unique functor which will be induced by F, actually unique functor F bar. Now how F bar is defined? F bar is defined from the quotient category to the preadditive category D prime. This is also a preadditive category, so the V and the functor F has actually induced a functor F bar such that F is equals to FOQ. So this functor F actually this functor from the preadditive category D to the preadditive category D prime factors into this induced functor and the functor Q, which was the canonical quotient functor. Q is canonical quotient functor. Okay, so this was the universal property, which is very straightforward. Now we will see actually the all construction we have done upon preadditive category. So I will leave a remark about all this construction if we talk about additive category instead of preadditive category. So remark. We are not going to prove this remark though. The remark is very interesting, so I thought I should mention this. So remark says this remark, or say you can say lemma. So if D is an additive category, then its quotient category d over I is also an additive category. Very trivial. We have seen in the case of preadditive category. Now this remark is saying the same thing in the context of additive category. So an additive category. So this was a remark, very beautiful actually. If you additive category is nothing but a pre-additive category that has all finite products, or you can say co-product, because in an additive category products and co-products are actually the same thing. So that was the remark which take things from pre-additive category to an additive category and works so well. So thank you for watching this video.